This podcast is going to talk about how to write net ionic equations. So a net ionic equation is really the simplified. We saw these when we looked at redox. It's really trying to focus on only what is actually happening. What is actually happening? Okay, in the test tube, in the reaction. So the steps, again, are on page 9. I have this written out for you on the first one. So what I just want you to do is add notes to what we're doing. So then when you go back and you're trying it yourself, you can come back and look at page 9 and kind of remind yourself of what we did and how we write it. So a balanced equation. Okay, these are all going to be double replacement reactions. So remember, in a double replacement reaction, you have a positive and a negative, because they're all going to be ionic compounds, positive and a negative. When we write double replacements, you never, ever, 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 did I say ever? Put two positives together. Two metals do not form a compound. So this positive is going to make a compound with that negative. This compound is with that negative. Remember, rules of ionic compounds. You always write the positive first and then the negative ion. So that means the cation goes first and then the anion, the positive, then the negative. I don't care how you think of it, but that's how you're going to see it, and that's how I expect that you should write it. So in this, remember, potassium we knew was a +1, sulfate is -2. Now I didn't need it in this one because it's already done. But if I only write, this is a reminder, what if I only give you half of the reaction, how to write the products. And over here, barium was a +2, nitrate was a -1. That is why over here in barium sulfate, because barium was a +2, sulfate a -2, that was why there are no subscripts over here. And they cancel each other out. And then potassium was a +1, and then nitrate was a -1. That is why it is just KNO3, because the +1 -1 canceled out, and that's why the 2 went here to balance the equation. Okay, that was a reminder on writing double equations. What you need to know when we're writing net ionics, you must have the states. You must have states. Now the two states you're going to see are aqueous and solids. And remember, a solid means the precipitate. Should have probably said that during the solubility rules. Solid is a precipitate. So whenever you found the solid, that means you know what the precipitate is. Okay, so you have to have states. It needs to be a balanced equation. Now here's a clue when you're writing these. I like shortcuts. If you see the word a solution, you mix two solutions. Solutions are always aqueous. When we have double replacement precipitate reactions, another shortcut, your reactants are always aqueous. You don't have to check the solubility rules for your reactants. Your reactants are always aqueous. You only have to check the solubility rules for your products. Okay, so that's the balanced equation. A few notes on that. Okay, now I'm just going to kind of erase what I have up here so far. Now let's focus on my overall ionic. So I want you to kind of look, what did I do going from here to here? So look at the states. If it's aqueous, that means it's going to separate. So you know what I'm going to do? I'm going to actually kind of draw this, because this is a good skill to have. So if it's an aqueous ionic compound, we know that it is going to actually conduct electricity. That's going to be an electrolyte. So there are going to be these potassium and these sulfate ions floating around, swimming around. Yes, there would be more potassium than sulfate. So in this beaker, I have these ions, because it's aqueous, they separate. So look at what you did. I did. But you will be doing. So this is where you start writing yourself a note. If aqueous, you have to write it down here, separate into ions. Okay, must have charges. You have to have charges. But look at what you're writing. You're writing an ionic equation. So you have to have pluses and minuses because that's what makes it ionic. It's not solid potassium in that beaker. That would get exciting. It's pretty boring. It's just the potassium ion. Okay, so look at it again. Barium separates. Okay, this 2 meant I had 2 ions. That's where that's coming from. This 2 meant I had 2 ions here. Barium is a +2, nitrate a -1. Remember, you have a reference table. The back of the periodic table helps you with these charges. Over here, same thing. Anywhere you see aqueous, you're going to separate into ions. It has to have charges, and it has the states. So you have charges and states. What if you don't put the charges? It would be wrong. So you have to have charges and states. Okay, now look at what happened here. So look at if we drew this. Okay, let me keep drawing. So look at what we had over here. We had some barium ions. And what else do we have in here floating around? Nitrates. That's why this would be a good electrolyte, because all of this, these aren't flying, they're not gases. This is saying they're all solution, and all of those are floating around in the solution. So both of those would be electrolyte solutions. Okay, so what am I doing then? I'm mixing this together into one big beaker. So what happens at the next stage then? It's the net ionic is what's really happening in that beaker. This is overwhelming, I'll be honest. The overall ionics, you may have to write it once in a while, but really my focus is to get to where we can jump to writing this without having to go through the overall ionic. So if you look at what's really happening, so potassium didn't do anything, it didn't change. Nitrate didn't do anything, it didn't change. So what really happened? The barium ion and that sulfate ion must have had some kind of attraction because they formed a barium sulfate solid. So that means now what I'm going to see at the bottom of the beaker over time, or it's going to get cloudy, you're going to make a solid. So at the bottom, you would see barium sulfate solid. If we let it sit, it's going to settle down and it's going to form a solid at the bottom. So that's why in a net ionic, it's bring down the solid, and it's what 2 ions made that solid. Or you can think of it, what ions were not, and you can cancel out the ions that weren't involved. And that's why we did not put those in. It's really just what actually happened. Well, we made this solid. How did we make this solid? It's because the barium ions and the sulfate ions. So again, you have to have charges. If it's a ion, you need charges, if aqueous. It should be balanced. This is balanced. But really is what made the solid. That's what a net ionic is telling me. What actually happened in that reaction. Now, we can't forget everything, and so what we start calling are spectator ions, and it's just kind of like if you were spectating in anything, in a dance, in an athletic event. You are just watching, you do nothing. So spectator ions, we call them the do-nothings, but they are still in this solution. So the spectator ions are still floating around those solutions. So this solution is actually still an electrolyte. That's why if we are collecting this precipitate and we filter it, we need to make sure we wash the precipitate, because we need to wash all of those spectator ions. They will go with the water into the filtrate, which is what you're collecting, but those ions are still there. So that's why if you ever do not wash it, this mass of this precipitate would actually probably be higher, because when the water evaporated, you're going to add some potassium and some nitrate to your solid. So they're there, they just don't do anything. So we call them the spectators. So my goal is to where you can get this, you look at what's making the solid, and then you work backwards to be able to write what the net ionic is. Okay, so let's practice this one, the bottom page 9, together. So keywords, notice I have solutions, silver acetate, strontium chloride. Is where I would have your periodic tables, because I know silver is a +1, acetate's a -1, strontium is in group 2, so it's a +2, chloride is a -1. So first we're going to write the balanced equation. So +1 silver, -1 acetate. I know it's aqueous, A, because it's a reactant, or B, because they're both solutions. I don't have to check. And let's see, I have strontium, +1, +2, chloride -1. Again, I know it's aqueous. Wow, that's a Q. Okay, now this is where we have to do double replacement. So +1 silver with a -1 chloride. That's silver chloride. I'm reminding myself I do have to check these. And then I have a +2 strontium, -1 acetate. That's why I need 2 acetates. Again, I need to check that. Okay. It doesn't matter which one. If you wrote strontium acetate first, that doesn't matter. Remember, the order you write the compounds doesn't matter, but I am writing my positives first. Okay, this is where we need your solubility rules. So you look at the back of the periodic table, you find chlorides. Most chlorides are aqueous. However, silver is a exception, so that means that's your solid. Okay, once you find your solid, you know this one has to be aqueous. You will never, ever, ever have 2 solids. Okay, side note, what if I have 2 aqueous products? What will happen if I have 2 aqueous products? That means you're not going to have a reaction. That means no reaction. You're going to dump those 2 things together, and you are not going to see anything. So you could have 2, possibly you could have 2 aqueous, that would mean no reaction. You'll never see 2 solids. That's not going to happen in the reactions you're going to see. Okay, overall ionic, oh, let's balance it. So then we have to put a 2 there, and we'll put a 2 there. Okay, overall ionic, remember this is where we look at our aqueous. So we're going to just separate it. This is the ones that take a lot of room. So we have 2 silver ions. I have 2 acetate ions, because that's what my balance equation told me. And then I have a strontium, which I know is a +2. And see your 2 here? That tells me I have 2 chlorides. All forming, okay, there's your solid. Remember, keep solids together. So when net ionics, you always keep solids, liquids, gases together. The only ones you're going to see right now are solids. But whenever we start writing these, you always keep solid, liquid, gases together. Then strontium would separate, and I have 2 acetate ions. Okay, that's the overall. Overall is kind of the pain. Net ionic. Now, let's practice jumping to the net ionic, because in an activity you're going to do, I'm not going to make you write all these overalls. I want you just to focus on the net ionic. So net ionic goes, okay, here's my solid. So kind of work it backwards. So I know I have this silver solid. Well, what 2 ions made the silver chloride? Well, it had to be your silver ions and your chloride ions. Okay, now some of you are probably noticing this 2, 2, 2. Yes, I could simplify that, and I could take that to just 1 silver plus 1 chloride goes to 1 silver chloride. Don't stress on that. It's still a balanced equation. So that is what's actually happening. The silver ions, let me sneak in my aqueous, and the chloride ions, it's like a love story. They found each other and they made the solid silver chloride. Okay, spectators, remember, spectators are which ions did not make the solid. which two ions are still in that solution, they're hanging out, and what ones, let's see. So it's really pretty much which ones did you not use. So go up here, what did I not use? Well, I didn't use strontium, and acetate also was not used. Now, don't worry about the coefficients in front of them, because we know there's really a lot more than one or two of those. We worry about coefficients in a balanced equation, but you don't have to worry about it when you're telling me the spectators. Okay, so if you look at on the next two pages, that's some practice for you. So you can always look back at your page 9 and reference it, and hopefully you have all of this good information. So this is where during some office hours, if you need some help, first you've watched these videos, and then I can help you if you're not quite sure how to do them. One thing on pages 10 and 11, let's just do one more practice on writing double replacements. So that's on number 2, page 10, number 2. So it's predict the products, balance equations, circle the precipitate. So in this, if we look, remember, it's a positive and a negative. I know that the calcium in here is a +2. You can write it down if you need to. I know nitrate is a -1. I know lithium is a +1, and I know a phosphate is a -3. All of that I could find from my periodic table. So now I have to make a compound between a +2 calcium and a -3 phosphate. Remember, swap, drop. All of these are going to be ionic compounds. So that means you're always going to be looking at charges, and you're always going to be using your shortcuts, swap and drop. So that means I have a calcium, it's going to need 3, phosphate is going to need the 2. We will have to use our back. I'm going to hold off for a second. Then I have a +1 lithium, a -1 nitrate. 1, 1 means it cancels out. Oops, see, I automatically, when I see anything with a group 1, I just automatically start writing the states down. Let's balance it. So I know to balance it, I'm going to have 3 calciums over here because I have 3 calciums. That gives me, if you look at 2 phosphates, 6 lithiums, 6 nitrates. That's why I have to have a 6 over here. Okay, using your balanced equation, that's a balanced equation. Using the back of your periodic table, now let's look at the compounds. I just automatically started with lithium. Nitrates are never solids. Lithium is a group 1, never solids. That's how I knew this was always going to be aqueous. That's my shortcut. I write anything with a group 1, I just automatically start writing aqueous. They're never my solid. Now let's look at your calcium phosphate. So calcium phosphate, and this is where I'm going back to what we had on this podcast. So look at your phosphates. Most phosphates are insoluble, which means they're the solid, which means they're precipitates. Check the exceptions. Calcium is not one of the exceptions. That means calcium is going to be your solid. And then it says, what is the precipitate? Well, the precipitate is the solid that you made. So that's what I'm wanting you to do on question 2, is just practice writing those double replacement reactions. I will hopefully see you in our office hours if you have any troubles. Again, send emails, send questions, put a question on Google Classroom, come to an office hour. I'm here to help, and that's bottom line, that's what I want to do, is just be able to help you. I will see you guys later.